These are your 9-6A notes, analyzing functions and modeling data. We have reached the point in Algebra 1 where we have finished studying all three of the major functions that we want to introduce to you as Algebra 1 students. Way back in first semester, we taught you about linear functions and exponential functions. And actually, exponential were second semester, but they were at the beginning of the year, around January. And then we just finished up our chapter on quadratic functions. And so just a quick little summary of each of those. Linear function graphs a line. And one of the forms of a linear function is slope-intercept form, y equals mx plus b. Quadratic function should look pretty familiar to you, is a parabola. And one of the forms is standard form, y equals ax squared plus bx plus c. And it's probably been a while since you've seen the exponential function, but these are growth and decay functions. Y equals a times b to the x. So the x is actually the exponent of that type of function. So what's going to happen here is pretty much you've done everything with these things. If I gave you all of the equations, you knew how to make the table of values, and then you could graph it. And so, but in reality, usually you have a table of values. You'd collect data, and then you look at the data, and from the data you decide, does this information, this data, model more of a linear pattern, a quadratic pattern, or an exponential pattern? And so based on those points, you can create a graph, you can create an equation, and then you can use it later on to make observations and predict in the future or go back in time and look at information. And so to choose a model, one of the ways that you can choose a model is by using a graph. You graph the given ordered pairs, and then looking at the graph, you decide, is it linear, quadratic, or exponential? So this is one of the ways that you can look at all the data that was collected, plot the points, and just look at it, give a quick little visual. So let's go ahead and try that with these three. So we're going to graph these ordered pairs, and then we're going to decide whether the data represents a linear, a quadratic, or an exponential function. So 1, 2, 2, 5, 3, 6, 4, 5, and 5, 2. And what I'm noticing here is that the data, if I were to continue that pattern, I'm just going to do a dotted line because that's what the book did. And I followed that pattern through. I'm kind of filling in some gaps there. I don't know if it's continuous or not, but that to me looks like a parabola. And so I would say that this data follows a quadratic model. So a quadratic function for number 1. For number 2, I've got the ordered pair -1, 6, 0, 2, 1 2/3, and 2 2/9. Okay, and those little fractions there are kind of a little key element there. When we did exponential functions will decline or they'll rise, but they always level out at 0. And so it won't cross that x-axis. It gets closer and closer. So this 2/3 and this 2/9. It's not always the case. But that's a good sign that the numbers are getting smaller and smaller, but not quite reaching 0. This is an exponential function. Okay. And so my Algebra 2 has just finished up a whole exploration using exponential decay and body temperature and cooling rates. Quadratic, things that follow quadratic paths. I'm thinking of like a height of a rocket going off. So it starts at the ground, it takes off, it's a flight pattern, it tops out, and then it's going to come back down. Or the flight of a baseball after it's hit. So a couple different things that you can look at that you can relate to. And the last one, we got -1, -4, 0, -2, 1, 0, and 2, 2. And based on my graph, I can kind of see that it's lining up in a linear fashion. And it's a linear function. All sorts of things involve linear functions. Anything like a price of something, or maybe how much you make per hour would be a linear function, that sort of thing. Okay, so that is one way to look at the information. But another way, if you don't want to plot points, or if the points are ugly, or maybe they're so big that you can't really tell the pattern, another way to look is not graphing at all. And to be honest, to set up a graph and make the coordinate plane and make all your labels of your axes, it gets a little annoying. So this is another way to quickly determine what the data is giving us. And it just allows us to say, should I look at linear? Should I be thinking of y equals mx plus b? Should I be concentrating more on something squared, like a quadratic? So looking at the data points, it allows us to focus in what type of equation should I be looking at. So I got to go over some terms here, and you might want to spend some time on this slide. Successive, it's kind of a weird word, but successive means consecutive or in a row, one right after the other. And so we're going to choose a model by using successive differences. We're going to look at these ordered pairs, and we're going to look at them as long as it's given in a row, as long as the change of x and the change in y are consistent. So as long as we count up by x's by tens, if the data is given where you count like maybe every 10 minutes or 10 seconds, or maybe by ones or twos. So as long as the x values are in a consistent pattern, you can use successive differences. And the first difference is just that. You're going to take the differences of the y values. We're going to subtract the y values of the data, one from the other. They're right next to each other. And we're going to do that through the whole table of values. And what this says, if the first differences are equal, so if you do that subtraction through the entire table and they're all equal, then the data represents a linear function, because that would represent a constant rate of change. And that's exactly what a constant rate of change is the definition of slope. So if your change of your y values is constant, the same, that means that you had a slope. However, sometimes it's not the same. So then what we do is we take all of those differences and we subtract the differences from each other. And so we look at the second differences. It's the differences of the differences. And when I'm talking about differences, I'm talking about just a subtraction problem. That's all I'm talking about, the answer to a subtraction problem. So if you go ahead and subtract the first successive differences and you realize that they are all equal, then the data represents a quadratic function. And so we don't have a slope anymore. We have something like y equals ax squared. We have something squared. If neither of those work, we stop subtracting and we look at a ratio. So we put the successive y values over each other and we write them as a ratio. And if they're equal, then it's an exponential function. And what I mean by that, the y values, if you take the second y value and place it over the first y value, and you get a number. It could be 3/4. It could be -4. But as long as when you put the third y value over the second y value, you get the same exact number, and the next one, and the next one, as long as it's consistent, then you know it's exponential. So linear, first differences are equal. Quadratic, the second differences are equal. And exponential, the ratios are equal. So let's go ahead, and we'll do that in just a second. But I want to also talk about what do you do with it after you say it's linear, quadratic, or exponential. What are we going to do from there? So you should remember this a little bit from before. This is going to be probably the hardest part. If it's linear, I want your brain to be thinking y equals mx plus b. We need to come up with an equation that represents those points. And just to review, you're going to plug in slope for m. And if you don't know how to find slope, you might have to look it up. And I can give you it really quick. The slope formula is the change in y over the change in x. It's a nice little formula. So you find, using the ordered pairs in your set, you pick two of them, you find the m value, you use one of those ordered pairs to plug in for x and y, you plug in m, and you solve for b. And you'll have an equation that works for all the data set. Quadratic, I know the quadratic equation is much more complicated than that, but we're just going to stick with the simplified form of the quadratic. When you get into algebra 2, you can do the bx plus c. But what we're saying is those are 0, very standard graph. This is going to have a vertex at 0, 0. And so when you do this, you simply plug in the x and the y from the table. So you'll plug in x, you'll plug in y, and then you're going to solve for a. So you have your access to all those ordered pairs. Solve for a, but you cannot use 0, 0. You can't use 0, 0 because when you square 0, you get 0. Everything would turn into 0. So that's one ordered pair that you're not allowed to use for x and y. And for exponential, if you figure out the data represents exponential, your brain needs to be thinking in terms of y equals a times b to the x. And so I put this here. This is one way, and I'll show you another way too. So if the data gives you 0, a, you have the a value, you can just plug it in. The a value is the y-intercept. So if you have an ordered pair, 0, a number, that's your a value. If they don't give you that, your b value is equal to that common ratio. So the ratio of r that you found that determined it was exponential is the base of your exponential function. So there's a couple different ways to write your exponential function. So let's go ahead and try this, and then you guys can try it on your own. So the first thing we're going to decide is if it's linear, quadratic, or exponential, looking at the differences in ratios. And then the second thing we're going to do is after we determine which function it is, we're going to write an equation. All right, so looking at these differences of this data, I'm going to subtract, and I realize that my x values are successive. Okay, I'm counting down. I'm getting bigger by 1. My x's are increasing by 1 each time. And so now I'm going to just subtract my y values. And so when I subtract my y values, I like to work backwards through the problem. So I like to say 2 minus 0 is 2. 8 minus 2 is 6. And so that right there tells me it's not linear. But I'm going to keep going because I'm going to do it again and subtract these numbers. So I need all my numbers. So now I'm going to subtract 8 from 18, and I get 10. And I'm going to subtract 18 from 32, and that gives me, I can't do my math right now in my head. Why can't I do that math? 32 take away 18 is 14. I wanted to say 14, but I didn't want to be wrong. Okay, so this right here gives me enough information to say not linear. Okay, sorry about that. So the fact that those numbers don't match tells me it's not linear. So the next thing I'm going to do is I'm going to subtract these numbers. So I'm going to take 2 from 6, and I get 4. I'm going to take 6 away from 10, and I get 4. And I'm going to take 10 away from 14, and I get 4. Now I worked backwards to the problem. You don't have to. You could work either way. But the fact that all of these are equal tells me that this is going to be a quadratic function. Okay, so now that I know it's a quadratic function, my mind is set to write an equation of the form y equals ax squared. Because like I said, we're going to keep them very simple for you guys. So we're going to pick an ordered pair. I can't use 0, 0, but I think this is a nice ordered pair here. Not too big, not too small. I'm going to plug in that ordered pair. So the ordered pair I'm using is -2, +8. I'm going to plug 8 in for y. A is what we're trying to find. And I'm going to square -2. I'm going to put parentheses around it because I learned in the last chapter, in last sections, that if you square a negative, it becomes a positive. And so 8 is equal to -2 squared is a +4 times a, and divide by 4, divide by 4, a is equal to 2. I'm not finished. Now I'm just going to plug that a value into the equation, and so I end up with my equation y equals 2x squared. So I said that it was a quadratic, and then I actually found my quadratic equation. If I plug in all of those ordered pairs, all of them should work. 0, 0 works. When I plug in -1, I get -1 squared, which is 1. 1 times 2 is 2. When I plug in -3, I get 9. 9 times 2 is 18, on and on and on. So you could always check your answer by plugging in the table of values and making sure that they work. Let's try the next problem. So number 5, my x values are going in a row. Okay, we're increasing by 1 each time. And so I'm just going to go ahead and subtract. So I'm going to do 7 minus 5 is 2. 5 minus 3 is 2. 3 minus 1 is 2. And 1 minus a -1 is 2. And so all of those are equal. That was the first time I did the subtraction, so therefore we're dealing with a linear function. So I'm going to go ahead and I'm going to think in terms of y equals mx plus b. And my slope, I can use my slope formula to find my slope. And so the slope is the change in x and the change in y. So I'm going to use these two ordered pairs right here. Now remember, your ordered pairs are actually up and down this time, so don't go side to side. So my first ordered pair is 1, 5, and my second ordered pair is 2, 7. So I'm going to do 7 minus 5 over 2 minus 1. 7 minus 5 is 2. 2 minus 1 is 2. I end up getting 2. Now if you look, my numbers, I went from the back all the way to the front, and that tells me that I got a positive 2. So you can actually see the change in my y values was a positive 2, and my slope is positive 2. The other thing I can notice here is that they actually gave me the y-intercept. So I'm going to use that, 0, 3. If that's my y-intercept, little b is my y-intercept, I'm finished. Y equals 2x plus 3. Now, if they didn't give you that ordered pair, all I would do is plug in an x and a y into the equation and solve for little b. All right, the last one, I think you guys can all probably take a guess. It's probably going to be exponential. Okay, I'm going to save you the time. If you can recognize, they got some weird fractions in there. I'm not going to subtract weird fractions. I'm going to look to see if there's a common ratio first. And then that saves me doing all that alpha math. And so what I'm going to do is I'm going to rewrite these as a ratio. And if you notice, as my x numbers are increasing by 1, right, they're going up by 1, my y values are declining. They are getting smaller. And so I'm going to take 12 and put it over 36. And that gives me 1/3. And I'm going to do it again. I'm going to take 4 and put it over 12. Notice I always work with the second number and put it over the one right before it. That also gives me 1/3. Now I'm going to work with 4 and 4/3. I'm going to put 4/3 over the previous number. Now that's a little weird, but if you actually type that into your calculator and you say 4/3 divided by 4, you end up getting 1/3. So it does simplify to 1/3. And lastly, you're going to put 4/9 over 4/3. And I want to show you a quick little trick to clean that up. If I multiply both the top and bottom by 9, and the reason I picked 9 is 3 goes into 9 3 times, and 9 goes into itself, I end up getting 4/12, which is 1/3. So they all became 1/3, and that tells me that I'm looking for y equals a times b to the x. My a value, if I'm lucky enough to have it, is right here, 0, 4. So 0, 4, whoops, sorry, 0, 4 is my a value, and that's my y-intercept. And so y equals 4, and my b value is 1/3 times x. I found my base by using my change in rate. Now you can plug in x and y and solve for b too, but I'm going to check my answer. Always check your answers with these. I'm really concerned that if you don't do it in the right order, that you're going to get 3 instead of 1/3. Do you see how you can get a bunch of 3s? Or in the linear function, my slope is 2. If it's supposed to be -2, you could catch that by checking your answer. So I'm going to plug in a nice one. I'm going to plug in -1 and 12. So when x is -1, I get 1/3 raised to the -1 power. We learned in chapter maybe 8 that that flips it and makes it 3. 3 times 4 is 12. It works. So there you have it. We got a collection of data points. You determine what models it. Is it a linear, quadratic, or exponential model? And then you write an equation of that information. All right. So really quick, what types of functions did we discuss? All 3 of them. And then you write an equation for the following data. Good luck.